In this video, we'll learn about symbolic and numerical integration in Python and examine their differences in mathematical algorithms and computational performance through visual analysis. As we know, Python's standard library doesn't include built-in integration functions. Instead, integration is handled through external libraries such as NumPy, SymPy, SciPy, and others. Symbolic integration gives exact results for both definite and indefinite integrals, but it's limited to functions that follow the integration rules we've learned. So basically, it follows the same manual steps we use when solving integrals by hand. The integration rules we've learned are used for simple functions, but for more complex functions, we turn to numerical methods. Numerical integration applies only to definite integrals and gives an approximate result. Let's look at two examples to see when symbolic methods work and when they fail. For integrand e to the x squared, no elementary form for the indefinite integral. For the definite integral, we can forget antiderivatives. Just apply numerical ways to get the approximate solution. If we modify the function by adding 2x, then we can solve both indefinite and definite integrals symbolically. For the definite integral, since we can have an exact solution by symbolic way, numerical way is not necessary. Here, we focus on integration functions available in SymPy and SciPy and compare four numerical methods: the Riemann Sum, Trapezoidal Rule, Simpson's Rule, and Adaptive Quadrature. In our previous video, we introduced the concept of Riemann Sum, an essential educational tool for understanding the definite integral, which represents the area under a curve. You see, these formulas look abstract or complex. Let's break them down and compare their performance to build a clear understanding. So now let's move to the next section, computing definite integrals. First, we'll apply the symbolic method from SymPy and four numerical methods from SciPy to two different functions, one smooth and the other with a sharp peak. This function, the graph, looks like a narrow mountain. The maximum happens at x equals 2. Now let's run this cell to import all the necessary packages. Then run this cell to show all the results. Notice that for the smooth function, all four numerical methods produce very similar results. However, for the sharply peaked function, the adaptive quadrature method clearly outperforms the others. Next, in the visualization section, we will compare three method pairs: Riemann Sum versus Trapezoidal Rule on a smooth function. Second, Trapezoidal Rule versus Simpson's Rule on a polynomial function. The third method pair is Simpson's Rule and Adaptive Quad on a function with sharp peak. The left side shows the manual calculations, while the right side is not focused on computing the actual integral values. It just provides a conceptual visualization of how each method works. Alright, let's start with the first method of pair. The Riemann sum estimates the area under the curve using a finite number of rectangles, while the trapezoid rule uses trapezoids instead. Let's quickly recall the area formula for a trapezoid. Here we choose a simple smooth function x squared. The partition number is 2, so 2 subintervals, 3 points. The delta x is 1. So n is 2, meaning we are using only 2 slices, either rectangles or trapezoids, for our performance comparison. Let's run the code. With only 2 slices, we are not focusing on accuracy. This visualization is for conceptual understanding, to highlight the differences in how these two methods approximate the area. So by the performance comparison, trapezoid rule is better than Riemann sum for smooth functions. Let's move on to the second visualization, comparing the trapezoid rule with Simpson's rule. Let's run the code. As you can see, Simpson's rule is more accurate in this case because it uses a quadratic fit to better approximate the curve. Here the degree of our function is 5, is greater than 3. If the degree is smaller, up to 3, then Simpson's rule is excellent, can fit the curve much better. This is our final comparison. Simpson's rule used a fixed number of points. Here we choose 12. It's like measuring with a ruler, where all marks are equally spaced. The quad method is like microscope, very smart. It zooms in automatically where needed, especially near peaks, here near x equals 0. We can use trapezoid or Simpson's rule to do the quad method. Here we use single application form of Simpson's rule. We estimate error on each subinterval. We will refine aggressively near the peak, near x equals 0. For the outer intervals, we don't need to do further refinement. In our simulation, let's stop the recursion at 14 intervals, so we have 15 points. Let's see the visualization around the code. So the Simpson's rule, we only choose n is 12, so we total have 13 points, 12 subintervals. That's why the arrow is big near the peak. We would need many fixed points to capture the peak. But for the smart adaptive quadrature method, here our recursion stops at n is 14, so totally 15 points, 14 subintervals. Result is already pretty good. Let's plot the distribution of these 15 points to show how they concentrate near the peak at x equals 0, where the function changes rapidly. This adaptive approach is smart. In regions where the function is relatively smooth, no need to split the interval further. But for the critical region, the function changes rapidly to do the refinement. So the fixed methods like Simpson's rule waste effort on easy regions because you see those points are evenly spaced. Again, our learning goal here is not to compute the actual definite integral or the exact area under the curve. Instead, we are using these visualizations to conceptually understand and compare how each method performs.